Every time you stream music, save a JPEG, or your phone strips noise from a call, one matrix factorization is doing the heavy lifting billions of times per second. For a 1000 by 1000 Fourier matrix, the naive cost is roughly 1 million multiplications, since n squared for n equal to 1000 is a million. The Fast Fourier Transform brings that count down to about 5000 by using the formula n over 2 times log base 2 of n. And the secret behind this dramatic speedup is a single algebraic identity. We start with the Fourier matrix f sub n. Every entry is a power of w, where w equals e to the 2 pi I over n, the primitive nth root of unity. Multiplying this matrix by a vector takes n multiplications per row times n rows, giving n squared complex multiplications in total. For n equals 64, that's 4096. For n equals 1024, that's over a million, exactly 1,048,576. The matrix looks dense and unstructured. There's no obvious place to save work. To find one, we need a single key fact about roots of unity. Here's the linchpin. The 64th root of unity, when squared, equals the 32nd root of unity. Squaring doubles the angle. So w sub 64 equals e to the 2 pi I over 64. Now square it. W sub 64 squared equals e to the 4 pi I over 64. Simplify the fraction by dividing top and bottom by 2, and you get e to the 2 pi I over 32, which is exactly w sub 32. This single identity links f sub 64 to f sub 32. Inside the bigger Fourier matrix, the smaller one is hiding. We just need to expose it. That identity gives us the central factorization. F sub 64 equals a block matrix with I, D on the top row and I, minus D on the bottom row, multiplied by a block diagonal matrix containing two copies of F sub 32, multiplied by a permutation matrix P. Three pieces, read right to left. The right factor P is the even-odd permutation. It rearranges the input vector so the even-indexed entries come first and the odd-indexed entries come last. P costs 0 multiplications. It's just memory addressing. The middle factor then runs F sub 32 on the even half and F sub 32 on the odd half independently. Two smaller transforms instead of one big one. The left factor combines the two halves. Here, D is a diagonal matrix of Twiddle factors, 1 w squared on up through w to the 31st power. Let's trace this on a length 8 vector. First, P sorts the input into evens and odds, x0, x2, x4, x6, followed by x1, x3, x5, x7. Next, F sub 4 hits each half, producing two length 4 results. Call the even half result E and the odd half result O. Now the left factor finishes the job. The top half of the output is E plus D times O, and the bottom half is E minus D times O. So we have two halves, one twiddle multiply per slot, and the sign flip comes for free. The result is the same answer as F sub 8 applied directly. Let's count the cost for just one level of this factorization. Two copies of F sub 32 cost 2 times 32 squared. 32 squared is 1024 and twice that is 2048. Then the diagonal twiddle matrix D contributes 32 more multiplications. Adding these together gives a total of 2080. Now compare that to the naive cost of 64 squared, which is 4096. We just cut the work nearly in half with a single application of the factorization. Notice the pattern. The cost dropped from n squared down to 2 times n over 2 squared plus n over 2. That is the recurrence relation, and nothing stops us from applying the same trick again to each f sub 32 inside. We've cut the cost once. Now let's do it again and again. Each f sub 32 splits into 2 f sub 16s plus 16 fixed-up multiplications. Each f sub 16 splits into 2 f sub 8s plus 8 more. We keep going all the way down to f sub 1, which is just the number 1. Trivial, no work. The recursion has log base 2 of n levels. Here's the beautiful part. At every single level, the fix-up multiplications across all the blocks add up to exactly n over 2. Level 1 has one block of size 64 contributing 32 twiddles. Level 2 has two blocks of size 32 with 16 twiddles each. That's 32 total. Level 3 has 4 blocks of size 16 with 8 twiddles each. Again 32. The same n over 2 at every level. Multiply n over 2 by log base 2 of n levels, and the total cost is 1/2 times n times log base 2 of n. Look at the savings at scale. For n equals 64, the naive method costs 4096 multiplications, while the FFT costs just 192. That's about 21 times faster. For n equals 256, it's 65,536 versus 1,024, 64 times faster. For n equals 1,024, over a million multiplications collapse down to 5,120, roughly 200 times faster. And for n equal to 2 to the 20th, about a trillion operations drop to around 10 million. That's roughly 100,000 times faster. Notice that the speedup column itself grows with n. That's the crucial point. The FFT isn't merely faster by a constant factor. The speedup ratio is 2n divided by log base 2 of n, which itself blows up as n grows. The advantage compounds, turning problems that were genuinely infeasible into ones that finish before you blink. One clarification before we close. The FFT computes exactly the same discrete Fourier transform as the naive method. Same matrix, same output, same numbers down to round-off error. Only the route changes, and the permutation P really is free. It's just pointer arithmetic, not floating point work. The Fourier matrix earns the title of most important complex matrix for 3 reasons. First, its columns are orthogonal, so its inverse is simply 1 over n times its conjugate transpose. Second, it has hidden recursive structure, the factorization we just built. And third, that structure reduces n squared work to n log n, wherever Fourier transforms appear, which is nearly everywhere in numerical computing. Cooley and Tukey published this algorithm in 1965, though remarkably Gauss had already discovered it back in 1805. Its arrival made spectral methods, digital signal processing, and modern numerical solvers for partial differential equations practical almost overnight. The same factorization wears 3 faces. As a matrix equation, it's the block form we wrote, identity and d on top, identity and minus d below, times a block diagonal of 2 smaller Fourier matrices, times a permutation. As a recursion tree, it's log base 2 of n levels of halving the problem, and as a butterfly diagram, it's the signal flow graph etched into every audio chip and video codec on the planet. 3 pictures, 1 identity. Squaring the nth root of unity gives the n over 2th root of unity, and the dense matrix splits cleanly in half.